So here we go. We're going to start the third section of Chapter 8, our Techniques of Integration chapter. And it's one of my favorite techniques. It's called Trig Substitutions. And it really confuses a lot of people, but after a few semesters teaching it, I'm hoping I can try to make it a little more clear. So let's just jump right into it. And I'm going to do an example right off the bat. So this is Trig Substitutions. All right. And the example I'm going to use to start with is this integral of 1 over t squared times the square root of t squared minus 1 dt. Okay. Now the first thing we have to do is consider what tools do we have available to solve this integral. Here we have a function within a function, right? And that leads us to believe, when we have a function inside of a function, we think chain rule. U substitution is the technique of choice, integration-wise, related to the chain rule. So if we picked our u as t squared minus 1, we would need the derivative of that present somewhere in here. But the derivative of this is 2t, and we don't have that. We've got a t squared, but not a 2t, so that's not going to work so well. We could try integration by parts. We could say, well, this is 1 over t squared and over t squared minus 1. Neither of these make a particularly nice integral or derivative, so that might not pan out well either. We've learned about some techniques for solving trig identities, and we're able to, with some shuffling around, use trig, but there's not even any trig in here. So the challenge then is really this radical, this quadratic factor here. Underneath this radical, that's our hassle. So we're going to make what's called what I would call a very clever substitution. And this is going to seem like magic, but I'm going to explain it after you see how it works. And I'll show you the trick first. I'm going to say that t equals the secant of theta. Right now you might think, what the heck, why would you possibly do that? And then as usually we do, we say dt d theta. The derivative of secant, remember, is secant tangent. And then so that means dt equals secant theta tangent theta d theta. And then this t squared, I've got a t, but I've also got a t squared that I'm going to have to deal with up there. I'll just put this in here too. T squared will equal secant squared of theta. All right. Why did I do that? Let's take a look. I'm going to rewrite this integral and make all these substitutions. This becomes the integral of, let's see, the 1 stays a 1, so that's going to be 1 over, and the bottom is t squared, so t squared is secant squared theta. And then this radical becomes square root of t squared minus 1, so that becomes this long radical here, secant squared theta minus 1. And then my dt becomes I'm going to put that on top, secant theta tangent theta d theta. Okay, now this seems worse, right? I always take a step back to the back of the room and say, have I made any progress? Have I made my life any better? Man, right now it's not looking so good. Until we remember that secant squared minus 1. How's that going to pan out for me? I remember one of my Pythagorean identities, and I hope you remember these too, is tan squared theta plus 1 equals secant squared theta. Well, that leads me to that tangent squared theta equals secant squared theta minus 1. So this part in here, let me highlight that in blue, really matches this part pretty well. Okay, so then I can come back up here and rewrite this again. So secant squared theta minus 1 becomes tangent squared theta. So this becomes tangent squared under the square root, right? So that just becomes tangent. So I'm going to really condense this quite a bit. So on the top I've got secant theta, tangent theta over secant squared theta, tangent theta, and then d theta. All right, now things are starting to look good because I can bring out the all-powerful red pen of cancellation. The tangents cancel here. This secant cancels out with one of that secant there. And so what am I left with? I've just got the integral of, let's see, this all cancels except for 1 over secant, which really equals, well, secant is 1 over cosine, so this just equals the integral of cosine. Right? And the integral of cosine, we know, is just sine of theta plus c. Right? So that, you know, we made this bizarre substitution that we never would have thought of to make, you know, take a nice variable and convert it to this bizarre trig function. Go through all this work and look, you know, everything kind of boils down then to just one really easy integral, sine of theta plus c. So are we done? No. I want t, not theta. Okay, so what did we say way back when? We said that the secant theta is t. So t equals the secant of theta. Well, when we see trig functions, we think of triangles. So I'm going to draw this triangle here and say if t is the secant, so really t equals 1 over cosine, so opposite or adjacent over hypotenuse. So it's hypotenuse over adjacent. So t has got to be hypotenuse over adjacent, which means this is t and adjacent is 1. Right? Hypotenuse over adjacent, t over 1, which is just t. Well, I know that a squared plus b squared equals c squared. So it shouldn't be too much of a stretch for you guys to agree with me if I said that this is t squared minus 1. Now, it's no coincidence that t squared minus 1 shows up back over here. Okay. Now, the answer to my integral, my original integral, was that, you know, it comes out to be sine of theta plus c. Well, what is sine? Opposite over hypotenuse. So my final integral, the solution of my integral, equals the sine, so it's root t squared minus 1 opposite over hypotenuse plus c. And I guess I should indicate that that's my theta in there. And so that's the final solution for this particular integral. All right, now, hand waving and magic. I told you guys we never want to believe in hand waving or magic. So let's look behind the curtain and see what really happened there. On the quiz recently, we talked about these Pythagorean identities. And I love the Pythagorean identities. I don't know why. Maybe because they're so confusing to me for so long. But one of them is sine squared of theta plus cosine squared of theta equals 1. I'm going to rewrite that as cosine squared of theta equals 1 minus sine squared of theta. Yeah, I also could have rewritten that as I could have solved for sine squared of theta. Sine squared of theta equals 1 minus cosine squared theta. All right. And then one of the other trig identities, Pythagorean identities, is 1 plus the tangent squared of theta equals secant squared of theta. And I can rewrite that, solve for tangent squared here, is tangent squared of theta equals secant squared of theta, let's see, minus 1, right? Now I'm going to stop right here. The reason I'm going to stop is that here I've got 1 minus something squared. I've got 1 plus something squared. And I've got something squared minus 1. Okay, so really, I've kind of got, if I'm looking at a number and a squared variable, I've got all my combinations. 1 minus the variable squared, 1 plus the variable squared minus 1. So these are the only 3 possibilities I have. So this whole chapter really should be called replacing ugly radicals. Replacing ugly radicals. So if I've got a few different radicals that look like, say, I've got a radical in my integral that looks like this, 1 minus x squared, I could replace that with x equals the sine of theta. And what will that give me? That gives me, let's see, yeah, I don't really have room to write it the way I have in my notes. That becomes 1 minus sine squared theta, which really equaled 1 minus sine squared is cosine squared theta, so this just becomes cosine theta. Now we have to think about this a little bit. What did I do here? This really became cosine squared theta, and so remember, cosine can be positive or negative, between 1 and negative 1, but I squared it to ensure it's positive, and then I took the square root to get it back down to its original kind of value. So essentially what I did here by taking a cosine squared, make it positive, take the square root again, it's a lot like taking the absolute value. Okay. Now let's do it over here. If I had another version, say 1 plus the variable squared, make sure that's a radical there. Well, what could I use? I had 1 plus something squared, 1 plus something squared. Oh, here, how about this one? So if I said that x equals tangent of theta, so I'm going to use x equals tangent of theta. What will that give me? It becomes 1 plus tan squared theta, which equals 1 plus tangent squared is secant squared. Take the square root of secant squared, and I get the absolute value of the secant of theta. Last one, I've got 1 minus this, 1 plus this. How about the variable minus 1? So if I had x squared minus 1, I would use, what would I use here? X squared minus 1. So I've got a variable squared minus 1. Oh, this here. So I'm going to use x equals secant of theta. And that makes my radical look like this. So it becomes secant squared theta minus 1, which really equals the absolute value of the tangent of theta. Okay. And I kind of crammed this all into one page here, so let me delineate this a little bit for you so you can kind of tell that these are 3 separate things. So these things here. Now we need to be a little careful, right? Whenever, because we've talked about this in class, when you're squaring things and taking the square root, forcing things to be positive, you got to think about what are sine and cosine. So I'm going to make a couple of comments here. We need to be careful. All right, and here's what I'm going to do. For case 1 over here, I'll call this number 1. For case 1, I'm going to say that I'm going to limit my theta to be between negative pi over 2 pi over 2. Okay, so I made a slanted fraction and a regular fraction, whatever. What does this do? So if I'm saying that x is sine of theta, okay, I can get my all possible values of the sine of theta. If I'm looking at this over here, I'm looking at this part of the unit circle, right? All my possible values of sine are within this region. You know, and that makes that ensures that it's a one-to-one function. So for any given value of sine, I can come up with one value of theta. Because if I included this half, then I'd have, you know, options. I'll explain that more in class. But this kind of has a built-in bonus for us. What is the value of cosine anywhere over here? It's always positive. It's always positive here. So I'm going to do in a different color, green, because this worked out pretty well for us. If I do that, if I make this limitation, this becomes just the cosine of theta. Okay, so that worked out pretty slick. If this is not crystal clear to you, I really hope you ask me in class. Option 2, corresponding with option 2, tangent of theta. Well, where can I get all possible values of tangent of theta? Oh, the same place. So I'm going to say that theta, again, is between pi over 2, negative pi over 2, and pi over 2, because I can get all possible values of tangent in this range. And, oh, lo and behold, the secant of theta, which is 1 over cosine, well, cosine is always positive, so secant is always going to be positive. So this, I'm going to get crazy here. Let's go orange. This constraint for number 2 means that the secant is always going to be positive, so I can drop the absolute value sign. For the third one, let's take a look at this. For our third, you know, type of ugly, for our third type of ugly radical we want to get rid of, I'm going to use secant of theta. Where can I get all possible values of secant? All possible values of secant comes where I get all possible values of cosine. So I really need to go between, is this still black? Yeah. I'm going to go from 0 all the way up to pi, right? But that becomes a little tricky because secant is 1 over cosine. So where do I have to be careful when I'm dividing by cosine? Dividing by 0, that's at pi over 2. So theta cannot equal pi over 2 here. And so that means that you know, I can't really, since my value of tangent is going to flip back and forth between the first and second. So really, okay, let's draw a picture of this. So this is this, you know, chunk of the unit circle here. My tangent is positive here, negative here. So I can't be so clean. I can't just get rid of my my absolute value signs here. So it worked really well for these two, but these two here. Now this is a subtle thing. It's important in some integrals, and I thought it's important to say. If this is a little foggy for you, please ask about it in class, and we'll talk about it more. Okay, now that we've got a little, we understand kind of how this trick works, let's see if we can apply it again to a real problem. And the next example I'm going to use is this one here. I'm going to take the integral of dx over the square root of 9 plus x squared. Okay, now something that kind of bothered me when I was younger was when this dx is on top. I kind of like the dx at the end, because remember, the dx is the base of these rectangles when we're doing the sum of all these rectangles, the Riemann sum. So I'm going to rewrite this just because it makes a little more sense to me to have it in the form 1 over 9 plus x squared dx. Now we got a number plus a variable squared, number plus a variable squared. So let's take a look back. Number plus a variable squared. Here we go. So according to my little cheat sheet that I inadvertently built, I'm going to say that x equals the tangent of theta, right? Number plus something squared, x equals tangent of theta. So x equals tangent of theta, I'm going to say x equals 3 tan theta. What the heck, 3? Where did this 3 come from? Well, what happens when I stick this in here? My integral becomes, oh, and then let's see, dx is the integral of tangent to secant squared. So dx equals 3 secant squared theta d theta, right? So my dx becomes a 3 secant squared theta d theta, and my radical becomes the square root of 9 plus, okay, but 3 tangent of theta, so that becomes squared 9 tangent squared of theta. All right, well, why did I put that 3 in there? Because if I factor out this square root of 9, my integral now becomes, still with a 3 secant squared theta d theta on top, and the bottom becomes root 9 times root, what's left here, 1 plus tangent squared theta. Well, 1 plus tangent squared, I know that's secant squared, so this becomes just secant over secant squared. That's nice. So let's do some cancellations here. I'll write this one more time before I cancel stuff out. So 3 secant squared theta d theta over 3 times, well, secant squared, square root, that's just secant of theta. So it just becomes this thing here, right? Now we get out the all-powerful red pen of cancellation. We can cancel out those 3's. That was convenient. And the secant squared, this whole secant cancels out that exponent there. So what am I left with? Just the secant of theta, right? So let's, this becomes just the integral of secant of theta. Now, right, the question is, what is the secant of theta? This is one you may have done in Calc 1, you may not have done, but it involves this kind of crazy trig identity. So I'm just going to skip to the punchline here and say the integral of secant equals the natural log of secant theta plus tangent theta plus c. Okay, and if you're confused about this, please ask me about that in class. Or you can take a moment to say, I think your book has this in chapter 6, maybe? 7? 6 or 7, I think. Your book actually does this for you. All right. But wait a minute. No good. I screwed this up. I told you I make mistakes in the lecture notes all the time. Wait. I can't believe I did this. But this is in terms of theta. Not x. All right, so we got to take a time out and figure out what is what exactly is theta. So I said that x equals tangent 3. Might as well erase that. X equals 3 tan theta, so that means that tan theta equals x over 3. So when we have, trig functions, that makes us believe that boy, that's a terrible right triangle. I'm really striking out here. Let's try that again. Let's make a right triangle here, Dress. Okay. So the tangent of theta, Opposite over adjacent, tangent, opposite over adjacent. So opposite over adjacent, which makes this one, let's see if I can write sideways on the tablet, is, let's see, 9 plus x squared. Whoa, is that a coincidence? 9 plus x squared, 9 plus x squared? No, I don't think so. So now we know that we're really looking for, I'm going to make this is called cheating. When you say I'm kind of almost done here and I put a dotted box. Sometimes when I come up with an important partial step in a solution, I'll put a dotted box around it to say this warrants a box, but it's not completely done. And now when you look at the notes, it'll look like I did that on purpose. Where are we here? We're trying to find the natural log of the secant. Well, the secant is 1 over the cosine, so it's hypotenuse over adjacent. So it's natural log of 9 plus x squared over 3 plus the tangent, which is opposite over adjacent, which is x over 3. So I can, same denominator, so I might as well just exploit that. The natural log of this fraction, root 9 plus x squared plus x all over 3. Now that gets a solid box. Alright, so that one included most of the tricks that we wind up doing with these trig substitutions. Alright, so with the hard one under our belt, I'm going to do just one more example, and we'll call it a day, call it a night, whatever your schedule is. So let's take a look at this one. Now I want you guys to really think along with me and see if we can figure this one out. So this is another example. I'm going to say the integral of x over root x squared minus 1 dx. Okay, x squared minus 1. A variable squared minus something. Is it on here? No. Here, a variable squared minus something. Here it is. So according to this little plan here, we should use x equals secant of theta. It's a variable squared minus something, x equals secant of theta. All right. Let's go forward. X equals secant of theta. So dx. What's the derivative of secant? Secant, come on, secant theta, tangent theta, d theta. All right, so we make our substitution. X is secant theta, and then we've got square root of x squared minus 1, so that's secant squared theta. And then we've got the dx, which is really a secant theta, tangent theta, d theta. Wow, is this thing huge. While secant squared of theta minus 1, right, is the same as tangent squared of theta. And so that gives us an interesting solution because we can't just ditch the absolute value there. So we got to keep that in mind. But let's rewrite this thing as secant squared of theta, tangent theta over the square root of secant. So this is tangent theta, absolute value. And then d theta, right? Well, we kind of lucked out here in that we get a tangent theta, and so we just have to be careful of signs, because if this is the absolute value and tangent happens to be negative, well then this could make a -1, so we just have to be aware of that. Now, since this is an indefinite integral, it's just some contrived mathematical problem. It's not like, what's the distance from, here to my buddy's house? It's, -7. Yeah, that would make sense. Here, we'll just ignore it. So we'll cancel that tangent out. That cancels out there, so we have just the integral of secant squared, which should make us pretty happy. Right, what does that equal? Well, that's the tangent. Okay, so the solution is tangent theta plus c. However, right, we still want to get back to x. So let's draw a picture of this. X is secant theta. So here's our triangle. If x is the secant of theta, that's hypotenuse over adjacent. Hypotenuse over adjacent. So that's x over 1. We've done one like this already, I think. So this becomes x squared minus 1, right? No coincidence. X squared minus 1. And so we want the tangent of theta, which is opposite over adjacent. Opposite over adjacent. So that'll give us, I think I did this wrong on my, my notes are wrong, but I did it right. So it pays off to leave my notes once in a while. So the tangent of theta really is opposite over adjacent, so this becomes x squared minus 1 over 1 plus c. All right. There you go. And that's it for trig substitutions. We will visit this again later. And some of you may have noticed I didn't necessarily take the easiest way to do this. So think about that. Maybe propose an easier way to do this in class. Thanks, guys. We'll see you soon.